So now we move forward to discussing some of the simple but highly useful circuits of operational amplifiers. And in this lecture, I'll be focusing on two main configurations. One is open loop amplifier and its utility, and then we will move on to negative feedback amplifiers. I'll explain what is a negative feedback, and then we'll discuss some circuits which are derived from this particular configuration. So an open loop amplifier. So before looking at this, what we can do is we can go over some of the important points or some of the important aspects of operational amplifier operation, right? So this is basically a slight recap from the previous lecture. And during this next couple of lectures, what I'll do is I'll keep repeating these main points or keep highlighting these main points before discussing analysis of any circuit, because it's very important that these points make a good imprint on your understanding. And whenever you look at the circuit, some of these points should be automatically recalled by you. So let's go over these. So first, the operational amplifier or the op-amp amplifies the difference of inputs at the two input terminals, right? So that's what an operational amplifier is. Its input stage is a differential amplifier, and the output is basically amplified signal of difference of the inputs at the two input terminals. And now some of the characteristics of a general operational amplifier. Open loop gain of an op-amp is very, very large. So ideally infinite, but let's say for 741, so the numbers I'm going to quote here are for 741. So for 741, the open loop gain is actually about 200,000. So very, very large gain. Maximum output voltage or the saturation voltage, as it is called, of an op-amp circuit. So that's the output, maximum output that it can deliver, is limited by the bias power supply providing plus VCCN minus VE. So that means the maximum output or the saturation voltage will be close to this. And as I explained during the discussion on characteristics of operational amplifiers, it will be slightly lower than these limiting values because of the forward drop in the transistors. The input impedance of an operational amplifier is again very high. And so again, ideally it's infinite, but for 741 it would be of the order of few mega ohms. And subsequently, therefore, very little or negligible current flows through the operational amplifier. Right? So again, look at this point very carefully and just remember it while analyzing the circuits. What we mean by saying very little or negligible current flowing through the operational amplifier is, now this should be looked at from the point of view of another characteristic of these op-amps, which we discussed in the last lecture, that is the offset and the bias current, input bias current and input offset current, and that is what we mean by very little. So the typical values we quoted there were like less than a microampere. So within the operational amplifier, less than a microampere current will typically flow, and we will see very soon when we will discuss the actual circuits that our typical input voltages, input signals would be of the order of millivolts to volts. And what that means is most of the current which is derived from the input signal source will not enter the operational amplifier. Right? So that's what we mean, and that's mainly because the input impedance is very high. Right. So the input impedance of an operational amplifier is very high, and therefore very little negligible current flows through the op-amp. The input, and so continuing from here, the input and output stages of an op-amp, therefore, so again recall that input impedance of an operational amplifier is supposed to be very high, ideally infinite, typically few mega ohms. Similarly, output impedance is ideally supposed to be zero, typically it will be few tens of ohms. Right. So the input and output stages of an operational amplifier, therefore, can be represented by the following equivalent circuit. Right. And what this circuit basically means is that since the input impedance is very high and the output impedance is very low, and the output only depends on the difference of the input signals multiplied by the open loop gain, as far as the impedance analysis is concerned, we can actually separate out the input and output stage. So the input stage would be represented something like this, that there are two input terminals which are connected through this input impedance, because this is the impedance that the signal power supply will face, right? And this is very high, so very little current flows in this circuit. Similarly, the output is simply the gain of the operational amplifier into multiplied by the difference voltage, so AOLVD, and now this would typically act, as far as the impedance analysis is concerned, we will take this as an independent power source within the op-amp, right, with internal resistance, which is then represented for any external circuitry as the output impedance of this operational amplifier, and this is very, very small. So the output stage is typically mimicking an ideal voltage source, whereas the input stage mimics an ideal load, right, with a very high impedance. Okay, so remember these points, and then we move on to the actual practical circuits of these operational amplifiers. So the first one, as we wrote down in the heading, it's the open loop amplifier. So let us see what it does. Now, so this is the circuit, and an open loop amplifier has, so the way we want to construct it, has only one input, and the other input terminal is grounded, right? So that's what it shows here. That and for in general, what I'm choosing is I'm choosing the pin number 2, and again, for in discussing all these circuits, we are mainly going to consider 741 as our choice op-amp. So I'll keep writing these terminal pin numbers just to, clarify that these are the pins at which in a real circuit you are supposed to provide the signals and make the measurements from, right? So for I741, pin number 2 is the inverting input, pin number 3 is the non-inverting input. Again, later on I'll probably omit this, but for any amplifier circuit, one must keep in mind that at pin number 4, negative bias, and pin number 7, the positive bias is always connected. If we do not connect the bias, DC bias, then the circuit is not going to give any reasonable output, right? So although we'll not be showing this in all the circuits, but it should be implicitly assumed that the biasing, DC biasing at given VCC values is always present. Okay, so one input at the inverting terminal and the other input is simply grounded. That's your open loop configuration with proper biasing, and the output is then taken from pin number 6. Now, if the input is given to the inverting terminal, then as the name suggests, it's inverting terminal, then the output will be out of phase with the input. And in a different configuration, if we suppose ground the inverting terminal and give our input signal at the non-inverting terminal, then the output will be in phase with the input signal. So this is what we know, and we can actually check this out also. Now, so now typically what happens is these operational amplifiers, especially the 741 or the other ones that we'll be using, these are generally used for small signal amplification. And now here it's important to define what is small signal, right? Again, why? Because the gain, as we saw, is very, very large. So one has to worry about what kind of signals we give and what kind of outputs we can expect. So these op-amp circuits are small signal circuits. And then what we mean by this small signal? So in practical terms, this means that the input signal will have a typical range from millivolts to volts, right? So that's our working input source. So we can take about a few millivolts input signal, or few hundred millivolts input signal, or about a volt input signal, this kind of magnitudes. Now, as the open loop gain of the operational amplifier is 200,000, right? At least the 741. Now, so let's say this is my input range. So even for a 1 millivolt signal, the output will exceed 200 volts, right? So I mean, in this configuration, because the VID is same as V gain. So let's say I give 1 millivolt, let's say DC voltage, then the gain of the amplifier is 200,000 as we have characterized. So the output is simply 200,000 into 1 millivolt, and that still would give me theoretically 200 volts, right? However, this 200 volts is simply not possible, right? Again, what we are saying is that it's an amplifier with a biasing which is limited to plus minus 15 volt. You give a 1 millivolt signal and you get 200 volts output, right? And that is just not possible because it violates energy conservation. You are giving the total input power is much less than what you expect to get out, right? So again, what this means is that in this configuration, in this open loop configuration, the operational amplifier will basically give you an output which is limited by this VCC, right? So that's what we meant by saturated output or V saturation, which is then limited by this VCC and will be typically like a couple of volts lower than this VCC because of the transistor forward drops, right? And again, if our input range is between, let's say, 1 millivolt to 1 volt, then the gain is so high that for any input signal, the output is simply going to be V saturated, because it would always like to go in this range, but it cannot. So it will be limited simply by the bias supply. And any input signal that you give, you will only get the saturated voltage at the output, right? So that would be the simple functioning of this operational amplifier circuit, open loop amplifier. So now, anyway, when we do the practicals, we will see how to make this circuit and what exactly to monitor there. Just for the sake of completeness of this discussion here, I am showing you a snapshot of the oscilloscope output for a 20 millivolt peak-to-peak sinusoidal input signal. So in blue, the waveform that you see is my 20 millivolt peak-to-peak sinusoidal input waveform. And the VCC, the bias, DC bias, is fixed at plus minus 9 volt. Actually, slightly lower than plus minus 9 volts because we are using dry cell batteries, and not necessarily a rated 9 volt battery will give you exactly 9 volts. So it's slightly lower, right? So with this, and the output, corresponding output at pin number 6 is then this yellow waveform, which you can see that to a very good approximation, there's simply a square wave output, right? And basically what this shows is that the op-amp output is always saturated and is independent of the input signal. So although the input signal is a continuously varying and slow varying signal, right? It's a sinusoidal waveform. The output is either plus VCC, minus VCC, or simply, at some point it's simply 0, right? Now, okay, so let's come to this point later, right? And this is the output. Now, what you can also do is, so this is the oscilloscope that you will be using, and we can actually make some quantitative estimates by looking at these waveforms, right? So first of all, the screen is graduated into a grid, right? Horizontally, it represents the time, and vertically, it's the voltage amplitude, right? Each division or each block represents a unit of time, and which is represented here. So you can see it like 500 microsecond, right? And it also shows the frequency of the signal. So right now the signal frequency is 1 kilohertz, and what that means is the time period of oscillation is 1 millisecond, right? And you can see that if I start from 0 and take one cycle of this input signal, it takes about 2 horizontal blocks, which represents 1 millisecond. So we can make some kind of quantitative estimates from here. Similarly, the vertical graduated scale represents voltage amplitudes. And again, for 2 different inputs, this blue one and the yellow one, the scales are given here. So each block here again represents a magnitude. And for the blue signal, each block represents 10 millivolts. So as you can see, the signal is restricted within one block, and when you actually use the signal, you can then try to observe and explain the deviations. But anyway, here I'll simply take it as plus minus 10 millivolt sinusoidal waveform, which is 20 millivolt peak to peak. And similarly, the output is now, the division is 5 volts, the yellow signal. So the output is basically something like more than 5 volts. So one block is 5 volts, and then you can try to count these smaller dots. So maybe let's say about 8 volts or something, or 7 volts. So plus minus 7.5 volts. And in fact, we can do a more quantitative measurement using the inbuilt feature of the oscilloscope, which is then represented here. So I can see it on the right side in the measure. So this shows V peak to peak values, peak to peak voltage values for this two waveforms. The blue one is channel 2 and the yellow one is channel 1. So the blue one, the oscilloscope measures 36 millivolts for a 20 millivolt peak to peak signal, and we will leave it till you perform the experiment to explain this. But for time being, just assume that this is 20 millivolt in actual case. The output waveform is corresponding to this is actually 15.2 volts. So that's about 7.5 volt plus minus, and that is your V saturation. So for a 9 volt battery, typically 1.5 volt is could be the bias, forward bias drop in the two transistors, right? These are silicon transistors, and that gives us a saturation voltage of plus minus 7.5 volts. So that's V peak to peak 15 volt, right? So this is the output. And now where we can use this circuit, what is the utility of this circuit, right? Because of course, it's not going to differentiate between any input signal. As soon as the input signal is more than 0, it simply goes to saturation. And depending on where we apply the input signal, it either gives you plus VCC or minus VCC. And in fact, in this circuit, I have given the input signal at inverting terminal. So as we can see, if the input is positive, the output is negative. When the input is negative, the output is simply positive V saturation, right? So what could be the utility of such a circuit? One, it can be used to compare the presence or absence of signal, right? So in cases where we are not really interested, what is the magnitude of signal, what is the time characteristics of temporal characteristics of the input signal, but all we want to know is if the signal is present or not, right? So as long as the signal value is greater than 0 or is different from 0, where 0 is my reference, is different from 0, I want an output. As soon as the signal exactly is 0 or just the reference value, I do not want an output, right? So I just want kind of a digital output, 0 or 1. And this kind of circuit, the open loop amplifier, can be used for this. So the output will be 0 only when the input is 0, and that's because the gain is very large. So as long as the difference input is 0, output will be 0. But for any other difference input in the range of millivolt, the gain is so large that the output will simply be saturation voltage. Right? Okay. Looking at this particular output, another utility one can think of is if I give it a sinusoidal input, what I get is again a fixed voltage. So we will worry about that later. But what we get is a square wave output. Right? So we can use it to some extent, or with a clever configuration, we can use similar such circuits, such open loop configurations to convert a sinusoidal waveform into a square waveform or a triangular waveform into a square waveform. So could be used to a certain extent in signal conversion, right? The qualitative behavior of the signal. However, again now something to note down here is it's not a perfect square wave in the sense that it's not minus V saturation and plus V saturation and nothing in between. There is, for certain time period, there is a rising and falling slope, and that is because of the slew rate limitation of the operational amplifier. Remember again, or observe again that we are working at 1 kilohertz. The input is not a DC input. We are working at 1 kilohertz, which means the changeover from a minus V saturation to plus V saturation or the other way around has to happen within a very short span of time, right? The signal changes polarity. Of course, the input signal changes polarity continuously, but it's still within 1 millisecond, right? So that, and within that period, in fact, within much smaller period compared to that 1 millisecond, the output is supposed to change polarity from plus 7.5 volts to minus 7.5 volts or the other way around. And that would be then limited by the slew rate of the operational amplifier. So in fact, that is how we'll also measure the slew rate, and that's where the slew rate starts affecting the performance. Now, as we saw in the previous slide, the open loop configuration is of very limited use due to its very high gain and extremely low bandwidth, right? I mean, as we saw, even for 1 kilohertz signal, it's the slew rate starts affecting the output performance, right? And anyway, typically the operational amplifier bandwidth is anyway like very small, less than 10 hertz. So such circuits will always have bandwidth limitations. However, a slight modification in these circuits opens up several possibilities which now control all aspects of analog circuit. So although the open loop configuration can be used to understand the characteristics of an operational amplifier, right? And it can be used in a limited sense to get useful, to make useful circuits. However, not all is lost, and with very little modification, a very simple circuit design, one can actually open up several possibilities, and these are the circuits which are at the heart of analog electronic circuits in all the devices which deal with signals and signal amplification. And what is that modification? So that modification is feedback circuits or feedback within the operational in the operational amplifier circuit. What do you mean by feedback? So a feedback, in very simple terms, is where a part or a fraction or the entire output signal, so part or full of the output signal, is fed back to the input end. Right? So what we are doing is we are giving some input to the operational amplifier, we are getting certain output, and then we are using intermediate circuitry to send this output back to the input and then look at the functioning of such circuits. Now, again, we can have two cases. So if the output is in phase with the input, so for example, if I am using open loop non-inverting input and then getting the output, and so the output is then in phase with the input, and if I feed back the same output to the same input, right, with some external circuitry, then this would be called a positive feedback. So where the phase matches. And schematically, you can represent it like this. So I give input at the non-inverting terminal. I know that the output is in phase with the input. And now using external circuit, I give some percentage or some fraction of this output back to the input terminal, right? So then at the input terminal, the actual input terminal, that is the non-inverting pin number 3, the signal is basically a superposition of your input signal plus whatever fraction it gets from the output. And both output and input are supposed to have the same polarity, so it will be basically the sum of these two contributions. So that is positive feedback. The other possibility is negative feedback, where the output is out of phase with the input signal. Right? So schematically, again, we can see it like this. So if I give the input at a non-inverting terminal, then the output is going to be out of phase with this input signal. And if the same is fed back again at this one, then the resultant signal here at the inverting pin number 2 would be the algebraic sum of this input and this output, where the output has a phase mismatch with the input. Right? So these are the two feedback configurations, and the different utilities or different circuits can be made by suitably choosing this black box, which represents what fraction and in which way it is connected to the back to the input terminal. So what we'll do is, for major part of this course, we are interested in negative feedback circuits, right? And for time, you can probably think of why the positive feedback circuits are not going to give us more or a variety of useful configurations. Rather, the negative feedback circuits give more options. But anyway, and we'll discuss this probably later. So with the negative feedback circuits, let us see what kind of circuits we can make. And the first one is an inverting amplifier. So we'll simply take our open loop configuration, which we discussed just now, with the input given at the inverting terminal, and we will use a negative feedback, a very simple negative feedback, to make to make a negative feedback inverting amplifier. So this is the circuit diagram for this. So again, you can see that it's similar to the open loop configuration, with the only variation that now the output is connected back to the inverting pin number 2, through a resistor RF. Right? So this is my circuit for inverting amplifier. The input signal is given to the inverting pin through a resistor RI, and the output is fed back to a resistor RF. So now let's see what kind of output this circuit will give, right? Because it looks a bit non-intuitive. So we'll see which way we can understand its working. But before that, let us again make some observations and remind ourselves of a few things. So in this circuit, the input signal is given at inverting terminal through an input resistance Ri, as you can see, and the non-inverting terminal is grounded. So the non-inverting terminal is simply grounded here. Fine, that's observation number 1. Since the input is given at the inverting terminal, the output of the operational amplifier is going to be out of phase with the input, right? So the output is out of phase with the input, V out here, and this is fed back through a resistance RF to the inverting terminal itself, right? So that's the feedback which is connected here. What about the operational amplifier? So the amplifier output, the V out, is simply going to be gain, the open loop gain of the amplifier, which is the characteristic of the amplifier, the operational amplifier itself, the op amp itself, times the differential input, right? So as far as the operational amplifier is concerned, we are not bothered with this V in. In fact, the V out is going to be the difference input which appears between these two pins. We are representing it as VID, and the characteristic gain or the open loop gain of the operational amplifier, which is very, very large, right? So AOL into VID. And the last point, the input impedance of the amplifier is very large. It's an operational amplifier, same 741. So its characteristic input impedance is very large, of the order of few mega ohms, right? And its effect is, or its implication is, that no current or negligible current flows through the amplifier, right? So again, recall that impedance, equivalent impedance circuit, where we said that since the negligible current flows through the amplifier because the input impedance is very high, so the input and output stage are actually can be considered disconnected. Okay, so some observations, some reminders, and now let's look at the analysis of, or the working, or analyze the working of this circuit again step by step. So looking at one thing at a time. Now let's switch on our input signal. So the input signal, so to begin with, the input signal V in will develop at the inverting terminal. So this will start coming here. So at pin number 2. The non-inverting terminal is anyway grounded. So at pin number 3, it's always 0 volts. Therefore, the initial differential input, right, to the operational amplifier is simply V in, right? So to begin with, right, see, so because unless there is some V out, there is no meaning of this feedback. So to begin with, at t equal to 0, V in appears at pin number 2. At pin number 3, you have 0 volts. So the differential input to the amplifier is basically VID, and it will be of the same magnitude as V in. So VID is equal to V in. And at this point, what will happen is, since the gain of the amplifier is very, very large, the output voltage will shoot towards saturation, right? I mean, that's what we saw in case of an open loop amplifier. So if there's any difference input, differential input at the two terminals, the output is simply going to be V saturation. So the output very quickly rises towards V saturation. Now, since the output is connected back to the input, part of this output voltage, which will also develop at the inverting terminal. So now at pin number 2, there are two contributions, one coming because of this external power supply, external signal source V in, and another one because of the V out, which is in practice going to be very, very close to V saturation to begin with, right? Okay. So this will add to this. So the inverting input will be basically sum of V in plus whatever generates at V out. However, this V out is going to be of opposite polarity or out of phase with this V in, right? So what will happen is, since the output is out of phase with the input, the resultant voltage at the inverting terminal, pin number 2, right? That's our inverting terminal, will start decreasing, and as the voltage or the potential at pin number 2 starts decreasing, since the potential at pin number 3 is always going to remain constant because it's grounded, so it's simply going to be 0, the voltage at inverting terminal will start decreasing, and so will the VID, right? So if pin number 2 voltage decreases because it's V in basically minus some fraction V out, then the VID will also start decreasing, and subsequently if V out starts decreasing, then because it's simply the output is simply AOL into VID, the VID start decreasing, so the output is simply AOL into VID, the V out subsequently will also decrease after some amount of time, right? So that's what now the feedback is doing. Initially V out starts with V saturation, but as the feedback kicks in and as the things settle down, the V out starts to come down. So in practice, very quickly, right? And later on, we will dwell over what is the time scale involved in this operation. But very quickly, the VID or the differential input will become so small, right? Because the V in and V out is basically V saturation. So it can actually compensate for V in as long as V in is not more than V saturation. So VID will actually become close to 0, right? And as soon as VID becomes close to 0, again recall back what we discussed in case of open loop amplifier, that for difference input close to 0, V out could be finite, because now the gain, although the gain is very large, the differential input is very, very small. So their product could still be a finite number less than V saturation. Right? So that's what will happen. Very quickly, the differential input will become 0, right? And such that the output will become finite. Or by finite, we mean less than V saturation. This will be, so at this point, this will be the dynamic stable point of the circuit, right? Where the V out will be some finite value. What will happen is, as soon as the V out becomes, takes a finite value, that means the VID becomes 0, the V out will not be sufficient to then compensate for whatever is the signal input here. And so the value here does not remain constant, but tries to be as close to 0 as possible. Right? And that's why I call it a dynamically stable point. Okay, so this is a general working of this amplifier circuit. Now we'll try to quantify it in terms of gain of this amplifier, right? So we'll try to see what is that V out value, right? Which is around which the circuit would give you a stable output for a given input signal. So what we have achieved with this negative feedback here is that the output will force the input at the inverting terminal to 0, such that it is equal to the input at the non-inverting terminal and VID is close to 0, right? So when we said that VID becomes close to 0, what that means is V2 becomes very, very close to V3. And since V3 is 0, that means V2 or the potential at terminal 2, signal at terminal 2 should also be close to 0, right? And that's what we meant. And that's what the negative feedback has helped us achieve, right? So The point to keep in mind, in general, once you have figured out this analysis, have convinced yourself that this is what the analysis would look like. After this, all you have to keep in mind is that the negative feedback in this configuration, in such amplifier circuits, will always force the signals at the two input terminals, pin number 2 and pin number 3, inverting and non-inverting, to as close a value as possible to each other, such that the differential input is close to 0, right? That's what the negative feedback does. Now for this particular circuit, since the value at V2 is being forced to become close to 0 because the inverting non-inverting terminal is grounded. So for this circuit, terminal 2, the inverting terminal, will become a virtual ground, right? So it's called a virtual ground because we are not connecting it to the actual reference ground through a conducting wire, but the feedback makes sure that the voltage value or the potential at this inverting terminal is close to 0. And in this scenario, for this at this steady state condition, we will call it as a virtual ground. So another thing to now remember after this point onwards is that a negative feedback in case of an inverting amplifier will force the inverting terminal to a virtual ground. So the pin number 2 will always act as a virtual ground. That means its potential is going to be, its voltage is going to be 0. And once we have established this, now we can estimate V out for a given V in. Right? So now since we know that this point is 0 and no current flows through the amplifier, so between input and output, no current flows through the amplifier. So because of V in and V out, all the current flow is going to happen in this external arm. Right? So once the V2 becomes, so the purpose of the amplifier, the operational amplifier in this case with the negative feedback, all it's making sure is that V2 or the pin number 2 remains a virtual ground. Once it has settled down at this value, then rest of the functioning is simply as if it's taking place between this external arm of the circuit. Okay. So we taking V2 as a virtual ground, we can see that the current I flowing through Ri, so because of V in, since this is a ground point now, there will be a current flowing from the source to the ground, and again it's inverting amplifier, so there will be a current flowing from the ground to this output, right, which will be taken as a another source with the opposite polarity, right. So if this is positive, then this is negative, and that way you can decide for the convention of flow of current, right. However, since this is the ground point which connects both these terminals, the current in the input arm will be same as the current flow in the feedback arm. Right? So this, because basically this is what it's happening. There is no potential drop here. So the current flowing between this input and output through this external arm is going to be exactly the same. Right? And if that is the case, then what we are saying is that this current in the external arm is basically V in minus V2 over Ri, which is same as V2 minus V out over Rf. And V2 is 0. It's a virtual ground, so it's 0. And what that means is V in over Ri is equal to negative or out of phase V out over Rf. So that's the current flow in my inverting amplifier. And now what I can do is I can find out the V out as a function of V in, or we can characterize this in terms of gain of the operational amplifiers. Right? So V out is simply minus Rf over Ri V in, right, from this expression, and I can get the voltage gain for this feedback configuration as V out over V in, the actual input voltage in comparison to the measured output voltage, and call it gain. So V out can be now written as voltage gain of the amplifier into the input signal, right? And where ACL, so I'm calling it ACL just to separate it out or distinguish it from the characteristic open loop gain of the operational amplifier, because this is not that very high open loop gain. This is a factor which is dependent on this resistive network. So ACL, or the closed loop gain of the amplifier circuit, and this is basically minus RF over RI. So what you see is that the gain of the amplifier now in this particular configuration is not, so the output is not simply input into the very large gain of the amplifier and that way simply becoming saturated, but something that depends on these external components, RF and RI. So one should note that the closed loop gain is now independent of characteristics of the op-amp, or the characteristic gain of the op-amp, and is only governed by this external resistors RF and RI, which can be suitably chosen by the user, right? So using this negative feedback, what we have done is we have achieved an independence from the characteristics of the operational amplifier. So although we are using the operational amplifier, and in principle, intrinsically, we are using its characteristics to achieve the performance of the circuit. However, once the circuit is in a steady state, the relation between the input signal and output signal seems independent of the operational amplifier characteristics, rather only depend, at least in terms of gain, only depends on this external factor RF and RI, which are now user controlled, right? So because the operational amplifier is a prefabricated IC, and for a given architecture, its internal characteristics cannot be changed. However, external elements like RF and RI are completely under user control. So the user has now a control over the gain of the circuit, right? And now this can be used as a versatile amplifying stage, which is user controlled gain. Okay. So I'll stop the discussion on this particular amplifier by showing you a simple circuit, which you will anyway make during your laboratory sessions, right? So this is a inverting amplifier circuit you made using IC741 with RF equal to 10 kilo ohms and RA equal to 1 kilo ohm, such that the closed loop gain is about 10, right? And this is my function generator. So I'm using this 9 volts batteries to use the DC biasing, right? And using a function generator to generate, I think in this case, I'm using 20 millivolt peak to peak input signal, right? So that's what it shows here, 20 millivolts, and I mean, these things will be clear to you later on. 1 kilohertz input signal. So again, the blue waveform is the input and the yellow waveform is the output. One thing is obviously clear, that the output yellow waveform is out of phase with the input. So that's a characteristic of inverting amplifier. In fact, that's what we mean by inversion, right? The output is out of phase with the input. And second, if you look at the scale of these two input signals, then the input signal scale is 50 millivolt, right? So typically, sorry, this is I think 200 millivolt. 200 millivolt input and output, right? So sorry, input. So the input scale is 50 millivolt, and the output scale. So both the signals look exactly the same because the scales are different. And what we can see is that the scales are 10 times differing by 10 times. So that tells us that the output is 10 times the input, right? Let's move on to the next circuit, which is an a non-inverting amplifier, right? So very quickly we can go over this also. So again, the same thing. We are still using negative feedback, but now the input is given to the positive terminal, that is pin number 3. Okay. So this is a configuration for a non-inverting amplifier, right? Where the input is given to the non-inverting pin number 3. So the output will be in phase with the input. However, the feedback is still on the inverting terminal, right? So that is why it's a negative feedback. The feedback, so V out is always going to be out of phase with whatever input is given at this pin, right? So whatever input is given at this pin will generate a V out, which is out of phase with the input here. So that's a negative feedback. A negative feedback will always connect V out or the output pin, pin number 6, to inverting pin, pin number 2. A positive feedback, on the other hand, would connect pin number 6 for 741, pin number 6 to pin number 3, right? So keep this in mind. However, for a non-inverting amplifier, the input now will be given at pin number 3. So this is the non-inverting amplifier circuit. You can proceed to analyze the circuit in the exact same manner as we did for the inverting amplifier. Simply keep in mind that the purpose or the implication of a negative feedback is that the output will settle at a value such that difference input is 0, differential input is close to 0, and that means the voltage at pin number 2 is same as the voltage at pin number 3, right? That's what the negative feedback does. So now in this case, since the voltage at pin number 3 is going to be V in, pin number 2, V2, will not become a virtual ground, rather it would try to settle down at a value which is same as V in, right? So that's the only difference that will happen in case of a non-inverting amplifier. Another characteristic, no current or negligible current, such that we can actually kind of omit it from the analysis. No current flows through the IC itself, right? So all the current between input and output will then have to be taken in terms of the current flow in the external arm of the circuit, right? So with these two key things in mind, I will leave this as an exercise for you to show that the voltage gain or V out over V in for this particular configuration, right, of the non-inverting amplifier is 1 plus RF over RI. So, one thing to note down is there is no negative sign because the output is in phase with the input, and it's slightly different. It's not simply RF over RI, is 1 plus RF over RI, right? So you can do the analysis on the similar lines as we did for inverting amplifier and try to get this voltage gain for a non-inverting amplifier, right? So these are the two circuits which now give us a user-controlled gain, and in this way they are highly versatile and can be and in fact are used into amplification stages of several electronic modules. Okay, what I'll do is I'll break this lecture 3 into 2 parts now. So at this point I'll just stop because there is too much to remember and too many things to go over. So let's take a short break here, and I request you to go over the working of both the configurations again repeatedly. So go over it as many times you think it's needed for you to understand it properly, right? And recall the points which are of utmost necessity. Right? You can also try your hand at this SPICE simulator, which I had described in a supplementary video earlier. You can try to design these inverting and non-inverting amplifiers and see the see the output, and then try to match it with your understanding. Record your observations. If you measure something out of ordinary, record it, and then maybe we can discuss it in one of the discussion sessions, right? And I would, so basically I was thinking that I'll continue this lecture further, right, in the same video, and you can take a short break here, go over the previous things, and then come back to the video later. However, here I have decided that I'll end this video here, and then I'll put that as a second part of this lecture 3, the further analysis and more circuits, which you should only go over or start looking at once you have understood the inverting and non-inverting amplifiers properly. Why we are emphasizing this so much is because rest of the circuitry, rest of the circuit design, rest of all the operational amplifier circuits are based on these two amplifier circuits. So if you understand these amplifier circuits properly, rest all becomes just an extension of the same analysis. So go over these things, try to use the SPICE simulator, right? And then only look for the second part of this video. Thank you.